In this video, we're going to talk about some exponential decay problems. Last time we talked about exponential growth. This time I'm going to focus on radioactive decay. And the last problem we'll have to do is something we call carbon dating. Let's start with number 5 from the textbook. The radioactive isotope of lead, lead-209, decays at a rate proportional to the amount present at time t. So we're going to call this A. dA dt is proportional to the amount A that's present at time t, and has a half-life, I abbreviate that T1/2, of 3.3 hours. Initial amount here is going to be 1 gram. The isotope is present initially. How long will it take for 90% of the lead to decay? So we want to find T such that A equals 1/10 of a gram, since 90% of the 1 gram has decayed. So I already showed you last time how to make this a linear differential equation. If I make this dA dt is equal to Ka. This also can be solved as a separable differential equation, and you'll get the same answer. I just want to show you that I can have 1 over A dA is equal to K dt, and that's ln of absolute value of A is equal to K plus C1. And then A of t is going to be e to the k plus c1 is equal to e to the k times e to the c1 is equal to c e to the kt, like that. So you get the same answer for what your exponential form is, whether you use separable or linear. There's lots of things like that in differential equations where you can use multiple methods to get to the same place. This chapter is called Applications of Linear Differential Equations. So linear modeling, I think, something like that. So that's why I was using the linear form and solving it by finding mu in the previous problems. But if you recognize that this was a separable differential equation and you wanted to solve it that way, you could do that as well. So our C is still going to be our A0 here. Let's just prove that to you. E to the 0 is C times 1. C is our amount, 1 gram. So A of t is equal to 1 e to the kt. And our half-life is 3.3 hours. So we have 1/2 of a gram at 3.3 K. And go ahead and tell you what I got when I figured that out on my calculator. 3.3 K is equal to ln of 1/2, and K is approximately negative 0.21004460002. So it's exactly equal to negative 10 ln of 2 over 33. If you would like to have an exact form of that answer, but this is what it is in decimal approximation, and that'll get us good enough because we're going to round to the nearest year here. So I'm sorry, hours, not years, hours, years to hour. So we're going to have A of t is equal to e to the negative 0.21004460002t. We want to find out how long t for the amount to be 1/10. So ln of 0.1 is equal to negative 0.21004460002 t. We're going to divide by that big nasty number. So that t is about, and this is going to be 11, and then we're in hours here. All right, let's move on to number 7. Number 7 tells us to use information from number 6, which I'll copy for you. The initial amount is 100 milligrams of a radioactive substance. It's present after 6 hours. The mass is decreased by 3%. So and if the rate of decay is proportional to the amount of substance present at time t, then dA dt is equal to Ka, leaving us again with, you can follow all the steps, but A of t is equal to A naught e to the kt. And our A naught was 100. So we're at that point there. Then let's go ahead and find the half-life of this. So let's find K. So e to the 6K is equal to 0.97. 6K is equal to ln of 0.97. And K is equal to 1/6 ln of 0.97. So K is approximately negative 0.00507,653,46. To solve for the half-life, I'm going to say that e to the k t needs to be equal to 1/2. So negative 0.0050765,346 is equal to ln of 1/2. And t is going to be exactly equal to ln of 1/2 divided by a negative, well, I'll say approximately because we rounded that, 0.50765,346. And I'm going to round this to the nearest half hour, or the nearest tenth of an hour is 136.5 hours. So again, you see that the half-life of these things here is quite short, and so that means these things don't stay in their unstable radioactive form for very long. I'm going to skip over number 9 because while it is an exponential decay problem, it is not the kind of problem that we're dealing with here with radioactive decay. It has to do with a vertical beam of light passing through a clear liquid like salt water, and you don't actually get a numerical value like this. It's a question about what percentage of the light is still visible at a particular depth. So you have to answer as a percent. If you want to try that problem, it should come out to be 1/10 of 1% of the light is visible, or it has the intensity of 1/10 of 1% of the original intensity. So, but I'm going to move on to number 11, which is a carbon dating problem, which is a very specific type of radioactive decay here. And they refer you to the article on carbon dating that's earlier, but they don't tell you which of the values to use for the half-life, since there's two different values. There's the Libby half-life, and there's the Cambridge half-life, I think is the other one. They're going to use the Libby half-life in this problem. So my half-life here is going to be 5,600 years. And that's a nice round number that we use in most of these problems. And we want 85.5% to have decayed. So that means that we want 14.5% remaining. So let's go ahead and write our equation this way. It looks a little different, but let's write our amount is equal to our initial amount times, and let's just write a base of 1/2 this time. And we're going to take the time and divide it by this half-life. That's an equivalent form to what we've been writing here. And so now let's go ahead and try to find out if I want A divided by A naught. That's going to be A divided by A naught. That's going to be my percentage that's going to be remaining. So that's going to be 14.5% is 0.145. It's going to be equal to 1/2 T divided by 5,600. And so we're going to take the log of both sides. I'll use ln here. Using log properties, this is going to come down front. So ln of 0.145 is equal to T over 5,600 times ln of 1/2. I'll go ahead and make this ln of 0.145 divided by ln of 0.5 is equal to T over 5,600. T is going to be exactly equal to 5,600 ln of 0.145 divided by ln of 0.5, and that is approximately 15,600 years. So we don't usually round anymore exactly in these carbon dating problems beyond the nearest 100 years, just because this is a little bit imprecise. because there's all kinds of other variables that aren't accounted for other than time, temperature, pressure, all kinds of other things that could be going on that would affect the decay rate. So we're assuming a constant decay rate, but it's going to be about 15,600 years. Here is how old this piece of burned wood or charcoal would be that we're examining from this archaeological dig site. All right. Some other things to note here that it talks about in the article is that carbon-14 has a very short half-life. It's only good at dating things that are very young within about 10 cycles of the half-life here. Otherwise, we get so little amount of carbon-14 left that it's hard to detect, or we're just going to destroy the entire sample of it when we go through our process of trying to collect it. And if we don't try and do that, we just try and measure the radiation coming off of it. You can't tell the difference anymore between the radiation coming from the carbon-14 and the just regular background radiation that's just there all the time. So carbon-14 dating, when we talk about carbon dating, it's really only good for about 60,000 years or less. So anyways, there it is. And so we can use some other types of dating like we have already talked about here with different types of uranium or lead or other radioactive materials that have longer half-lives. Anyways, there you go. That kind of wraps up this discussion here. We'll have some other some other exponential decay models, specifically Newton's law of cooling, that I'm going to talk about separately. I think you'll really like that one to see that there's some practicality to this when we talk about taking hot liquid like coffee and letting it sit, or taking a cake out of an oven, or taking something out of the freezer and letting it thaw, or something like that, and letting something come close to room temperature. So hope you find that interesting. We'll do some examples of that when we come back next time.